Okay, thank you for the introduction, and I'd like to start by thanking the organizer for their kind invitation. I'm very glad to be speaking here, and sorry that I can't be there in person. I should start by saying that everything I talk about is joint work with Shuang Miao from Wuhan University, and also in part with Sijue Wu from the University of Michigan. Okay, so let me start by giving a short outline of what I'll talk about. So I will be talking about this hard phase fluid with a free boundary, and the eventual goal is to discuss the well-posedness when coupled to Einstein equations. But what I will do is I'll start by just first setting up the general background of the types of relativistic fluids we're considering. I'll say a few words about the general case, and then I'll quickly specialize to the case of aerotopic fluids, and quickly then to the hard phase fluids, which is what's the topic of the talk. And like I said, the eventual goal is to discuss the well-posedness when coupled to Einstein's equations. But to motivate what goes on, I'll start by discussing a related work, which is a well-posedness in the case of a relativistic fluid on a fixed background, specifically the Minkowski background. So that's the first part of the talk, and there, in fact, I'll also draw some comparisons with the Newtonian case. And okay, after discussing that, I'll come to the case of Einstein's equations and coupling to Einstein and discuss that at the end. Okay, so let me start. Let me start with just the notation. So in the case of when we're doing Einstein, I'll probably use M and G for the background, and when we're using Minkowski, I'll use M instead of G. For this is when the background is fixed, and box will always be with respect to just the background metric that we're working with. So in the case of Einstein, we'll be G. In the case of Minkowski, with respect to M. Okay, so that's just a quick word on the notation. So let's discuss what the relativistic fluids are. So there's two kinds of fluid quantities that we'll discuss. Is the fluid velocity, which is U. It's a vector in space-time, which is unit, u mu is -1, and it's future directed, time-like, right? It's -1, it's time-like, and it's unit and future directed. And then there's the thermodynamic variables, of which there's quite a few, but most of these will eventually quite quickly drop out for us. We're not interested in the most general case, but let's just write them. So there's a number density of particles, which is n, pressure P, energy density rho, entropy S, and temperature theta. And they're supposed to satisfy some laws of thermodynamics, which are given as these differential equations. And like I said, these are mostly not so important to us. We'll quickly specialize to a more restrictive class where these don't enter, not all of them enter. But an important quantity is the sound speed, or more precisely, the ratio of the sound speed to the speed of light, which is at constant entropy, is given by the square root of dp d rho. And this will always be between 0 and 1, where 1 is the normalized speed of light. Okay? But we're allowing it to equal the speed of light. In fact, we'll be eventually interested in this case. Okay, so that's the notation for the thermodynamic quantities. And let me now also describe what are the driving equations for this. So the driving equations are these two these two conservation laws, the vanishing of these two divergences. So what are these? T is the usual energy momentum tensor, which is given by P plus rho u mu u nu plus P times the inverse metric. And I is the particle current, which is n times u mu, where n was this number density. Okay, so and then the equations are again divergence T is 0 and divergence I is 0. And this is for the fluid, and if we're coupling to Einstein, then of course it will be the Einstein equations as well, which is just G plus 1/2 G scalar is the energy momentum. Okay, so those are the equations. And like I said, now we're going to specialize quickly to a more restrictive class, not completely the complete general class of fluids that I discussed above, but the aerotopic fluids, which are the following type of fluids. So it's the case where where the pressure is a function of the density only. So it's an invertible function. So you can write everything in terms of just one of these. So P will be a function of rho, which is an increasing function. And in this case, it's convenient. The equations will take a nicer form if I renormalize the fluid velocity U in the following way. Instead of considering U itself, we'll consider the following renormalization, e to the fu, where f, capital F, is given as follows. It's the integral of rho plus P from 0 to P, where I'm being rho as a function of P, as above. So with this renormalization, I define capital V to be e to the fu. I'll often just refer to this capital V still as fluid velocity, even though it's not exactly it's the renormalized version, but I'll still call it the fluid velocity, and I often will not use U so much anymore. And just to set the notation, I'll write the magnitude of V squared for minus mu because this U was time-like. Okay. So it turns out that in this with these assumptions, the equations take a pretty nice form, which is the following. So after some calculation, one arrives at the following two equations, basically for the divergence of T being 0 and divergence of I being 0, which is one is this momentum equation, which is just nabla VV plus 1/2 gradient V squared is 0. And the other one is the divergence of GV of V is 0, where this G of V is some function which depends on this magnitude V. The exact form of the function depends on the equation of state relating P and the pressure and the energy density. But this GV in terms of those is given as follows: P plus rho divided by norm V squared. Let me just quickly go back and tell you that here I define V, this absolute value V, or the capital F equivalently, as a function of P, but this is an increasing function. So conversely, I could think of P as a function of V as well, right? So there's really only one of these that comes up. So this magnitude V essentially, P and rho can be, P is a function of rho, and these can all be viewed as a function of this magnitude V. So this function here is just some function of this magnitude of V here. Okay. So these are my two. These turn out to be my two equations basically for the rest of this talk. And okay, so I think that's what I wanted to say. And these look very much like the standard non-relativistic Euler equation, at least formally, right? They look something similar. Okay. All right. So that was the general case of barotropic fluids, and now I want to discuss an even more special case, which is what we will be working with for the rest of this talk, and namely this hard phase fluids. So what are the assumptions for this? I'll first discuss the general assumptions, and then I will come back and say what I mean by this free boundary problem, what with this being the free boundary problem. So first of all, we assume the fluid is rotational. So it's the V is the gradient of some scalar function. And importantly, we assume that this sound speed is equal to the speed of light. So this ratio is equal to 1. And specifically, these are the equations of P and rho in terms of this magnitude V. P is 1/2 norm V squared minus 1. Rho is 1/2 norm V squared plus 1. And this function G that I was discussing in the last slide becomes constantly 1. Okay. So what happens to the equations in this case? I'll come back and say a few words about why this model, but let's just take it for now as it is, and let's see what happens to our equations. So here was our equation, and you'll see that if I said this G equal to 1, if this is equal to 1 in this hard phase, then this equation just becomes divergence V is equal to 0. Right. So that's what's going to happen in this equation in this case of the hard phase fluid. Okay. All right. So in this case also this will use the notation sigma squared. In this case, sigma squared is known as the enthalpy for this gradient of this magnitude of V squared. Okay. So these are the general assumptions of this hard phase fluid. So you see that it's going to be curl free. The D of V is 0, and like I just discussed, when G is equal to 1, the fluid is also going to be divergence free. Okay. All right. So now I said this is a free boundary problem. So what is the free boundary? So let omega be the fluid domain, and regardless of whether we're working in the case of Einstein or just on a fixed background, this fluid domain will always be an unknown. So the idea is to find the fluid domain and this velocity, etc., such that certain equations are satisfied inside the fluid domain and some boundary conditions. So for this, to be able to do this, one has to also find, one cannot do it in a fixed domain, one has to find the domain for which such a thing can be found. So that's what makes it a free boundary. So what are the boundary conditions precisely? So let me rewrite again the equations in this case of this hard phase model. So the entire equation is reduced to the following few equations. First just the equations and then the boundary conditions. The equations are, again, like we said, divergence v is 0 and curl v is 0, dv is 0. So those are the two equations. And then what are the boundary conditions? So there's two boundary conditions. One is that this sigma squared, which we define to be minus v mu, is 1 on the boundary. So if we go back and think about, for example, the pressure and how this relates to, there was all of these things were functions of each other. We could write the pressure as a function of sigma squared, etc. And if we look back at that, what this is saying is that the pressure is 0 on the boundary. So if we think in terms of the classical Newtonian case, this is equivalent to this condition that there's no surface tension in the boundary. Okay, so this is that's the condition that this sigma squared is 1 on the boundary. The other boundary condition is that the velocity is tangential to the boundary. This 4 vector, this v is this renormalized velocity, which is, of course, being tangential is the same as the original velocity being tangential to the boundary, which one can think of as saying that particles which are on the boundary at any point will at any other point will also be on the boundary. Okay, so those are the two boundary conditions which determine the boundary, which make this a free boundary. Okay, and of course, if we're coupling to Einstein, then there's also the Einstein equations, right? Where inside you have to have some matter, and outside this has to be vacuum. Okay, so that's it. There's one other condition that needs to be satisfied for this to make sense, and if it's satisfied initially, at least locally at the time, it will be satisfied also. But I'll come back to this. It's that the gradient of sigma squared, dot gradient sigma squared, has to be positive on the boundary. The meaning of this is essentially that as you go towards the fluid, if you write it again in terms of the pressure, as you go towards the fluid, if you go inside the fluid, the pressure increases. I'll come back and say something about the significance of that. And of course, I didn't write, but if you're coupling to Einstein, then constraints have to be satisfied also. Okay, so those are the equations in the case of hard phase and the boundary values. Okay. Maybe a few remarks about why this model. First of all, I should say that it goes by a few other names as stiff or incompressible also. Naively, it looks divergence-free, curl-free. So I guess that's why they call it divergence-free, because they call it incompressible. But of course, it's different because it's this divergence is the space-time divergence. But the reason we mathematically are interested in this is that it captures many of the general features, many of the important features of a much more general class of fluids, both relativistic and non-relativistic, but in particular, for example, in this relativistic case, this more general class of barotropic fluids that I discussed, I think this hard phase model really captures the essential mathematical features, and on the other hand, it's much easier to see the structures here, and it's much cleaner to understand, I think, what's going on in this set. Okay, so those are that's the mathematical reason. On the other hand, this is of independent physical interest, and my understanding is that it's supposed to be an idealized model for this situation where there's this gravitational collapse, and in that case, this mass energy density is supposed to exceed the nuclear saturation density, and the speed of light of sound is expected to reach the speed of light. I'm not going to say too much about this. I just wrote down some names of people who consider this, mainly to say that we're not the people who come up with this model. Like this has been of interest to people who are interested in this from a more physical point of view. It's not just a mathematical toy. Okay, so those are the reasons, but at least mathematically, like I said, it captures many of the essential features of more general classes. Okay, so that's a few words about the model. Okay, and now I'm going to talk about this first. Like I said, first I'll talk about this fixed case of a fixed background, and then I'll come back to Einstein. So for the fixed background, again, I'll denote the metric by M. It's just Minkowski, and box is the Minkowski box. And okay, so the equations again reduced in this case to the following. This is now in this case we have a preferred set of coordinates. I will work with the rectangular coordinates in R1 plus 3. So divergence B is 0, dV is 0, and the domain is an unknown, right? It's part of the unknown omega. And we want the enthalpy to be 1 on the boundary. We want V to be tangential. And like I said, we want the pressure to increase as we go towards the, so it's 1 on the boundary and then bigger than 1 inside. Okay, so that's what we're looking for. And the result is, of course, that if you give me the right type of initial data, there will be a local and time solution. What do I mean by right type of initial data? First, that this condition 8 is satisfied. This was this condition here, that as you go inside, the pressure increases. I'll come back and say again a few words about this when I discuss the proof why this is important. The other point I have to say is that, okay, this is an initial boundary value problem, so there has to be some compatibility conditions on the boundary, which one can write down just by looking at the equations, but those have to be satisfied to have reasonable well-posedness. And finally, that this is not an optimal regularity result. It's high regularity. We're not too careful about regularity. Okay, so I want to say a few words about the proof and aspects which are related to the case which when we couple to Einstein. But before I say that, maybe I should say a few words about related works. Also, so there's two classes really of these free boundary problems that people consider. There's the liquid model and the gaseous models, corresponding to the following scenarios. Liquid being when there's this jump in the density across the boundary. So from the inside, the density doesn't go to 0, but then outside we have 0 density. While gases are the ones where the density goes to 0 from the inside also, and they have their different difficulties. They're not they're different. They're quite different in that sense. But okay. Regardless, there's been quite a few different approaches for considering these problems, and as far as I know, the first well-posedness in either of these cases for this relativistic fluid, the first full well-posedness for relativistic fluid in either liquid or gas model was due to Olenek. And then in the liquid case, there were other works. There was work of Ginsburg in the case of some additional smallness where we proved a priori estimates. And then much more recently, there was work of Ginsburg and Lindblad, maybe a couple months ago. Again, this is everything in this slide is on a fixed background, right? Not coupling trans. For a fixed background, which was not the Minkowski background. And then in the gaseous model, there was there's other works. There are these works which are constructions of special solutions, not well-posedness, but existence sometimes with symmetry, sometimes without symmetry of certain solutions, like Makino and Rendell. Then there's a priori estimate works by Hajek, Schkaller, and Speck, by Shuang, Flock, Masmoudi. And again, more recently, there was a well-posedness in the gaseous case by Visconti, Freeman, and Tatar. Okay, but so let me discuss this from the point of view that I'm interested in for the rest of the talk, which are the aspects, like I said, which come in when we couple to Einstein. But to do that, I actually want to draw a comparison with the Newtonian problem. So I want to take a couple of slides to just discuss the analogous Newtonian problem. what is the analogous Newtonian problem? And so I'll use tildes to denote every quantity that's Newtonian, right? So it would be this is at least formally, the analogous problem would be the incompressible rotational fluid, where this is of course quite different in the sense that some of these operators which are hyperbolic in the relativistic case become elliptic in this case, and that's essentially why I want to compare to point this difference. But okay, so the equations are like this. So this time the difference is that this v tilde is not a space-time vector; it's just a spatial vector, right? It's a free vector. But the equations are divergence free, curl free. Again, we're looking for an unknown domain where the pressure is 0 on the boundary, and this vector, this time 1 comma v tilde, because v tilde is now just a free vector, is tangent to the boundary. Okay, and this is again the momentum equation that vt plus v dot nabla v is minus gradient of the pressure. Okay, so this condition that I've been saying, that as you go inside the fluid, the pressure increases. It's this Taylor-Stein condition. It's known in the Newtonian case already that if you don't have this can lead to instabilities, and you may not have well-posedness. But in this rotational case, for example, assuming gradient v squared is strictly greater than 0 on the boundary, by taking divergence of this equation, half lemma, you can see that this is satisfied on the boundary. That minus the normal derivative of the pressure is strictly positive, assuming this. Okay. So again, every tilde quantity corresponds to the Newtonian case. Okay, and tilde is the normal to the Newtonian boundary. All right. So those are the equations. And how does one prove a priori estimates for this? So this is due to Wu, 9799. And the way she did this is that she took a material derivative to the momentum equation. So material derivative, I mean dt plus v dot nabla v, and one derives this second order equation on the boundary. Now the point is that here it's curl divergence free. Of course, if it's not curl free, if it's not rotational, there will be some lower order terms, which is not so significant. But in any case, let's just look at again this model, which is rotational and compressible. So you take a derivative, a material derivative, you get this equation. So if you know the velocity on the boundary, you know it inside just by harmonicity. And this equation on the boundary is quite nice. Why is it quite nice? Because first of all, that this is since this is harmonic, this normal derivative here is a Dirichlet to Neumann map, which is a positive operator. Okay, and this condition that I've been talking about, that this dpdn on the boundary is negative, or minus dpdn is positive as you go inside, the pressure increases. This comes out precisely in the equations to the coefficient of this Dirichlet to Neumann map having the right sign. This is a positive number, positive function. Okay, so the operator here is quite nice. Of course, this is not linear, but at least one can think that there's hope for proving energy estimates, in the sense that if I were to multiply this by this dt being the material derivative of v, this is a positive operator, and it would give me some control of a maybe half derivative on the boundary. Okay, because this is harmonic, right? Because this is a nice elliptic equation inside, and this is the Dirichlet Neumann map. So that's great. So at least the left-hand side seems to have some nice structure. On the other hand, there's the gradient of the derivative of the pressure on the right-hand side. So to see that this is a quasi-linear equation, one has to understand this nonlinearity. And the key to understanding this is, again, ellipticity. Is that, again, this dt of the pressure, this material derivative of the pressure, satisfies elliptic equations. Okay, in Sijue Wu's approach, what she does is that she actually uses singular integrals to write this explicitly, to actually write this dt of the pressure explicitly in terms of the fluid velocity by using singular integrals. But this is at the heart of it is, again, ellipticity, that but using singular integrals to explicitly write it, which gives a lot more structure in the case, right? It actually can explicitly see that this is quasi-linear, and also see more about the structure. On the other hand, if you're just interested in this local well-posedness and say you're not able to use singular integrals if you're in a different context, for that particular aspect, there was a different approach to do in Lindblad, which instead of explicitly finding this dt of the pressure, they looked at the elliptic equation satisfied by them and just used estimates. So one can again see that they satisfy elliptic estimates. The pressure itself satisfies an elliptic estimate at the level of the derivative of the pressure of the velocity. The material derivative of the pressure satisfies another elliptic equation rather, and they both satisfy the boundary conditions because crucially because the material derivative is tangential to the boundary. That's the free boundary condition. So if P is 0 on the boundary, dt of it is also going to be 0 on the boundary. So they satisfy Dirichlet type elliptic equation, and one can use these to recover estimates for this dt of the pressure, which appears on the right-hand side of the equation. Okay, so that's the general approach. But okay, so the key points that I want to say is you take one material derivative to the equation, to the momentum equation, you get this equation which has where you can prove estimates using elliptic structures, both for the Dirichlet-Neumann map and for the right-hand side. Okay, so what happens now if one tries to do the same thing in the case of this relativistic fluid? So again, I'm going to use dv for this time for the material derivative, d mu v mu. And again, I emphasize that here we have a preferred set of coordinates. So I view the rectangular components of my fluid velocity as my unknowns, right? So these are all in the rectangular coordinates. Okay, so again, this enthalpy is constant on the boundary, which means that its gradient is in the normal direction when it restricts to the boundary. And this pressure increasing towards the fluid, again, tells me that if I write the gradient of the enthalpy as minus an, this a will be a positive. Okay. So again, this is like the sign of this Dirichlet-Neumann map having the right, the coefficient of it having the right sign. Okay. So now I take the momentum equation, I take a material derivative to it, a dv, and it becomes the following equation. So formally, it looks very much like the Newtonian equation, where dv squared plus an nabla n of v is this one derivative of dv sigma squared. And unlike the Newtonian case this time, this v doesn't satisfy an elliptic equation inside, but it satisfies a box equation. Okay, so I have a coupled wave boundary and interior wave equation, and this nabla n is no longer the standard Dirichlet-Neumann map. Rather, it's this hyperbolic version, but because this the box that's 0. Okay, so then we ask what can we do? And likewise, this dv of sigma squared, which is like dv of the pressure, this no longer satisfies an elliptic equation. This too satisfies the wave equation with Dirichlet boundary condition. So again, sigma squared itself, the enthalpy satisfies an equation at the level of one derivative of v, quadratic in one derivative of v, and it's constant on the boundary. Again, because dv is tangential to the boundary, if I differentiate this equation here, I will get that dv squared is 0 on the boundary. And one can compute that this dv squared also satisfies the box equation at the level of one derivative of the fluid velocity and two derivatives of sigma squared itself. Okay, so I have basically everything that was elliptic turned into a hyperbolic equation. Okay, so how does one prove estimates for this? Okay, it turns out that first of all, again, this Dirichlet-Neumann map, which is hyperbolic, can again be used to derive an energy estimate. Of course, again, one has to understand this better. This is quasi-linear, but roughly it goes like this: that by multiplying by dvv, one is able to obtain the following control of the following type of energy. That one derivative of v inside is like the usual wave energy, plus on the boundary we're able to control one material derivative of v. Okay, again, this a being positive is the sign condition, which guarantees that this term agrees in sign with the other term, right? But so here, when I put a little t here, I'm restricting to the x0 equals to t constant slices. So those are the that's the kind of energy that one obtains. Let me just illustrate this in a simplified model. Why this is okay. Let's just consider for a minute this very simplified model of a cylinder. So you suppose you have box u equals to f. For us, this f would be 0. Really, let's forget about that. And then this is like the normal derivative. So d squared t plus dr of u is 0 is some other source term. And then you imagine this is on an exact cylinder. Let's say, imagine you multiply by dtu, then you get some indeterminate terms. For example, on the boundary, you get the term dt du dtu dru, and in the interior, the usual energy identity has a gradient of dt nabla u. The point is that when you integrate by parts, the two indeterminate sign terms cancel each other. Okay, so you end up with a coercive energy essentially. So you get, this is the type of energy that we have. Okay, this is the type of energy that we control. Okay, so that's roughly the idea. Now, in controlling this, for us, for example, this f was 0, but this f here was again one derivative of dv of sigma squared. So the question becomes, how do I control that? Because now, again, unlike the Newtonian case, this satisfies a wave equation rather than an elliptic equation. Okay, so how does that go? So again, so this is the type of thing that I need to control. And again, we have a wave equation with Dirichlet boundary conditions. Okay, and again, by an appropriate multiplier identity, which is not just dv sigma squared, you have to add certain normal component to your multiplier for an appropriate alpha. You multiply by the right thing, but I won't go through the model case again. One can write up a model case, but and of course, I'm ignoring all the nonlinearities that one has to control, but roughly one gets controlled by such a multiplier of the following quantity: the usual energy, right, which is just one derivative on any fixed omega t, and then an integrated energy, which is exactly the type of thing that we need to control, right? So an integrated equation energy on the boundary, right? Not everywhere, but only on the boundary. So this type for the Dirichlet wave equation, one can choose this multiplier to get control precisely of this type of thing. So together, this is, of course, one has to go prove high regularity, etc. But these are somehow the two key points of starting this process. Okay, for doing energy estimates in the case of this fixed diagram. Okay, so I said that mainly to say that because I want to now come to the case of coupling to GR, and I want to say see what we can do there. Okay, so ideally we'd like to set this up in a way that we can at least carry out the fluid part the same way, but maybe the metric part will be a little bit different. Now, what are the difficulties? One is that we've been working with these rectangular coordinates where we don't have the rectangular coordinates, so we have to find an appropriate replacement where the fluid quantity satisfy the right equations, and then of course then we have to check if the curvature comes in the right way in the nonlinearity for the fluid equations or not. Okay. So really the main point is to find the right candidate for the unknown such that the fluid equations have essentially the same structure as before. And okay, so the result is again that given initial data satisfying the right constraint and compatibility conditions, local and time solutions, and again high regularity. Okay, and before I discuss again what the process is, maybe I'll say a few words about existing works. Okay, so for this class of free boundary problems that I've been talking about, the only other well-posedness result I'm aware of is in the case of elasticity, which is a work due to Anderson, Orlinik, and Schmidt. While in the case of fluids, I don't know any well-posedness, or a priori estimates, but there's works by Rendall, Kind, Ehlers, Frederick, and Frederick on less on the fluid side, but this type of fluid formulation that we do, but more on this maybe constructing some solutions without really tracking the boundary. Or when I said less on the fluid side, I mean less on the free boundary part. I guess there's less on how to deal with this free boundary, but there's some general formulations of the equations to try to get nice looking equation, but there's not so much on tracking what happens really to this free boundary as far as I know. Okay, but there's this, of course, right? There are some interesting works in this. Okay, so how does it go? So this is the setup. So first of all, we work with Lagrangian coordinates in the following sense that we choose coordinates t, x1, x2, x3, such that the partial t is our original fluid velocity, which in terms of this capital D is just v over magnitude g. Okay, so that's our choice of coordinates. And now what we want to do is that instead of the rectangular components of the fluid, which do not exist here, we want to expand in an orthonormal frame and view the components of V in an orthonormal frame as the unknowns. But somehow the idea is to choose an orthonormal frame such that the equation looks the way we want. This is the gauge that we have to choose, and we choose it in this way that we start with an orthonormal frame. Initially, E00 is -1, EI tilde is for 1, 2, 3 is equal to 1, and then we parallel transport this along the fluid flow. Okay, and this fluid is tangential to the boundary. Okay, so we parallel transport along the fluid flow this frame, and then we expand the fluid itself in this frame. Okay, I'll come back and say why this choice is important. It's not unique. I think one could put a lower order term here, and there's certain advantages to that and certain disadvantage. So certain things simplify if I put a different right hand side, and certain things become more complicated. But the main point is that I need this to be an almost parallel transport in terms of regularity. I need this to be a lower regularity on the right hand side in a sense that I will describe. Okay, so that's the setup for this. And before I come to the fluid equations in terms of this frame, let me say what else happens. So there's the geometric quantities to control, and for the geometric quantities, there's really two types of these geometric quantities. There are the frame vectors, right? So for the frame vectors, I need to control the coefficients of these frame vectors in the components of them in the coordinates that I'm working with. So the components of this EI in these coordinates, so basically EI mu is what I need to control. Then there's the connection coefficients, gamma ijk, which are the usual connection coefficients. Nabla EIJ is gamma ijk ek. So I need to control those. And then there's the curvature tensor. Okay. And I'll come back to the curvature tensor later, but if one goes through the conditions that we've set, this parallel transport, the first two classes, the components of the frame vectors was the connection coefficients will satisfy transport equations which are tangential to the boundary, because this fluid velocity is by assumption tangential to the boundary. Okay, so this dt, remember that this dt here was normalized to be dt is normalized to be just the fluid velocity, or the normalized this way, v over norm v, which is also u, right? So it's tangential to the boundary. Okay, so dt of E is at the level of one derivative of so theta, again, remember theta was this V was theta I pi. So this theta we should think of in terms as the fluid velocity essentially. So it's at the level of one derivative of the fluid velocity and at the connection coefficients. What about the connection coefficients? The connection coefficients, one time derivative of them is again at the level of one derivative of the fluid velocity and the curvature tensor. So here this R is not the scalar curvature, it could be an arbitrary component of the curvature tensor. Okay. So that's the regularity of the connection coefficients and the frame coefficients. Okay. So let me come back to the curvature tensor itself later, but now let me go and study the regularity of the equations for the fluid velocity. Okay. So let me just quickly go back and recall what the equation was in the case of the fixed background. In the case of the fixed background, here was the equation, right? The fluid velocity satisfied this type of equation: dv squared plus 1/2 the hyperbolic Dirichlet-Neumann map of v was gradient of this dv sigma squared. Okay, so in the case now of GR, it's in this frame that we've chosen, it's going to be something similar. I've started with the interior equation. Box of theta I is going to be something of this form, which is at the level of one derivative of the fluid velocity and connection coefficients, and up to one derivative of the connection coefficients. So when I write d is the same thing as partial here. Right? D is the same as partial. So these are all scalar functions now, right? That I'm working. Okay, so that's the interior. It's not zero, but it's some nonlinear wave equation. And in the inside, what do I have? In the inside, I'm sorry, on the boundary rather, I have the following equation, which is, this is similar to the term that we had before, one derivative of dv sigma squared, right? And then there's another term. The other term is at the level of one derivative of sigma squared with velocity and gamma itself. And here's where the choice of gauge is important, that if one works within a different gauge or an arbitrary gauge or in coordinates, arbitrary coordinates, one sees more than just the connection coefficients. One would see the derivatives of the connection coefficients. So the important point of the choice of frame that we made, of this gauge that we made, is that the derivatives of the connection coefficients don't come up here. And that would kill the regularity. If the derivatives of the connection coefficients came up here, this would not allow us to. This would prevent us from closing the estimates, right? So that's why we choose to parallel transport the frame, right? Because there's a second derivative in v here, and that's essentially going to make a derivative of the connection coefficients appear otherwise. Okay, so once this is there, okay, like I said, this is the main thing, right? That no derivatives of gamma appear on the boundary equation. Right? Inside they appear. Okay, but once we have this system, then okay, so we can try to do something similar to as is the fixed background. Of course, it's more nonlinear, but okay, we can try a similar method to try to prove estimates for this. And then how about again, there's the main term here, which is dv of sigma squared, one derivative on the boundary. Again, these satisfy a wave equation in the inside. Again, of Dirichlet type, both sigma squared and dv of sigma squared. There's new terms. Sigma squared is at the level of one derivative of the fluid velocity and the connection coefficient. And for dv of sigma squared, you also see the curvature on the right hand side and the types of things that you saw before also. Okay, but those are the equations for again, it's a Dirichlet type wave equation for sigma squared and dv sigma squared. So we can hope to use related techniques as in the fixed background case. Okay, so then the remaining equation that is completely new in this case is the curvature equation. So how do we deal with the curvature? So the difficulty with the curvature is that there's a discontinuity on the boundary. There's inside you have material, and this is in this liquid case, this density doesn't vanish as you go from the inside to the boundary. So so you have okay, you have this issue, but regardless, let's ignore that for a second. We want to use the Bianchi equations. Let's say I look just in the interior or just in the exterior. I don't pay attention to the boundary for a minute. I have the two Bianchi equations, which on the in the inside I would have a source term for this divergence equation, while in the exterior I would have vacuum. I would have zero. Okay, so we want to use these to set up. We want to view these as a hyperbolic system and prove estimates for the curvature in this way. But okay, now we have to deal with the boundary. And the point is that we will not view these equations for any curvature tensor, any component of the curvature tensor, but rather we will always contract with two vector fields which are tangential to the boundary. Not our frame vector fields, but something constructed out of our frame vector fields. So we have to construct these out of the frame vector fields because they don't remain tangential. They're just being, we've already fixed what these are by parallel transport. But we construct these out of the frame vector fields, and we consider only the components of the curvature tensor where the last two components are tangential. The point being that the original Ricci-Einstein equations are at the level of the second derivative of the metric, and we see this discontinuity on the boundary. But when the two of these are tangential, one can check that only at most one transversal derivative of the metric appears in the expression for the curvature, right? When I put two tangential vectors here, and with that, so if I were to contract these two equations with, say, xl, yn, right? Then I could, after I commute, I could view these as a first order hyperbolic system with source, which is L2, right? So this is still a weak equation, but it has a nice L2 right hand side. So then I could prove estimates for the at least L2 norm of the following components of the curvature tensor, where the last two components are tangential. Okay, but once I have that, then I use the symmetries and the Einstein equations themselves algebraically to recover the remaining curvature tensors, curvature components. Okay, so the only differential equations for the curvature that we consider are the ones where the last two components are tangential. Everything else is recovered algebraically. Okay, so that was this last equation. So maybe in the last couple of minutes that I have, I'll just say a few words very briefly about higher regularity, and then I'll stop. Okay, so these are the equations, and then I want to prove higher regularity, and the idea is as follows: that I want to preserve the structure of these equations, and it turns out that the best way to do this is to just commute again material derivatives with everything. So I commute a dv. Okay, every equation is a scalar equation the way we've written it, and I just commute material derivatives. dv, remember, was dv was my derivative in the direction of p, which is tangential to the boundary. Yeah. Okay. So why should I be able to do this? And the idea is that after I commute dv, I can use elliptic estimates to recover everything else. For example, the main operator on the boundary is dv squared plus 1, or a over n nabla n. So if I have control of higher order dv's, this means that I have control of one normal derivative on the boundary. So if I view the box equation that's satisfied by theta in the inside, it's as if I have control of a normal derivative. So if I view the box equation inside as an elliptic equation with the dv's and with the time derivatives somehow on the right hand side, then I have control of the normal derivative. So this is like an elliptic equation with Neumann boundary conditions that can recover elliptic estimates. So what I need is to control higher dv derivatives. Okay, I'm not going to go through the elliptic estimates, but let me just explain how one would control higher dv estimates. Okay, so suppose I take a dv derivative, for example, to the boundary equation. Turns out that now the curvature appears on the right hand side. So here I'm going to have an r, among other things, and so when I try to estimate one extra derivative of theta in L2, so the second dv derivative, that's what our boundary energy gives us. Then I will be facing, this is really also integrated in time, but I'm not. This is also integrated. There's also a time integration here, I guess, which are different, right? But it's but anyway, so I will face the curvature in L2. Let's say I use just a very rough trace estimate. I go to the derivative of the curvature inside. Okay. So then I have to see what my curvature equation gives me control of. Curvature equation itself gives me control of the L2 norm of the curvature, but now I'm commuting 1 dv, so I will have control from my curvature equation. I will have control of 1 dv of the curvature. So the question becomes, now I want to use control of 1 dv. Control of 1 dv, I want to use it to control any derivative of the curvature. Again, I view those Bianchi equations as elliptic equations, and I recover control like this, right? Basically, I'm able to control one derivative of the curvature in terms of a material derivative, and the one derivative of the curvature I control using the equation for the curvature. So I have to commute a dv with the curvature equation, and one checks that main term on the right hand side is again of the order of one derivative of the dv of the fluid velocity, which is part of my my second order energy for theta. So in other words, this whole thing closes, right? There's no loss of regularity in this, because the basic energy gives me the basic energy for dv of theta was basically gave me two things. In the inside, it gave me one derivative of dv theta squared, and on the boundary, it gave me dv squared of theta squared. So I started off by trying to estimate this, and all I need was the interior part of this. And because of the time integration, I'm able to close this essentially. Okay, this is a very rough outline, but and then there's elliptic estimate that one has to prove this. But okay, I wanted to convey the main ideas. I think that's what I tried to do, and thank you for your attention.